Hello grade 11 GED 2019-2020 students. Still we are in topic 3, oscillations, lesson 3.1, simple harmonic motion, and this is the second lesson for simple harmonic motion. For today we are going to describe simple harmonic motion using equations with graphical expressions of displacement, velocity, and acceleration. Now displacement time graph looks like this is a sine function because we have the sinusoidal wave, so that's why the graph can be represented by a sine or cosine function. Now let's here our y-axis is representing the displacement x. So, and here above the equilibrium point we have the positive direction of displacement, and here we have the negative direction. Our x-axis representing t, and as we know, when we have here the maximum displacement, this is the equilibrium point and this is our maximum displacement. Whenever we are looking for the value of displacement, we have to go our y-axis. The x-axis will give us the values for time, and as you know, here the object is completing one period, and here half a period, and here it is only completing 1/4 of the time period, and here 3/4 time period. And we have the most important thing here, the equation. The displacement at any time. Now it's very easy to get the displacement at certain points, like here the displacement is 0. It is 0 here, maximum here, again 0 here, maximum value 0, and so on. But what about at any other time, like if the for example object is here? What about this displacement? How to get it? We have the function x equal to x naught sine omega t. At any time, now this is the amplitude, and we have here our angular frequency. So at any time t, we can get our displacement x. Let's us make things more clear. Like now, if we have, for example, let's talk in terms of circular motion, and we will know why. If we have an object like a pen here and moving in a circular motion on this circumference, and if we have here a screen, so, and a light source here, so we can get the projection of this object here on the screen. So the pen can be here, 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 yeah, or any other way. So if it's here, here it will be the projection on the screen, the shadow, I mean the shadow of this, and when it's here, we will get the shadow here. If it's here, again, and if it's here, the maximum other point to the other side, and when it's here, back, this is the projection of the pen. Now, as we see here, the motion is starting from this point to maximum up, again this point, maximum down, again to this point. So although the pen is moving with a circular path, but you are getting the projection as simple harmonic motion. I think this maybe picture will give you a very clear relationship between the circular motion and the simple harmonic motion. That's why let's again go with the circle. We will do some math here. If this object is here or the mass is here at its equilibrium point, then it can come here to its maximum displacement, which is x0. But what about if it's here at any time? So now this is the angle theta. Here, when the object is here, we want to calculate this displacement, which is x. Now, sine theta that you know here, for example, if we are taking the pendulum, simple pendulum, okay, here is our theta, and the path is an arc, a part of this circumference. So we are talking in terms of theta, angular displacement. So our sine theta equal to here, this is the opposite side x over x0. From here we can get x equal to x0 sine theta. And our theta, as you know, that this is from the circular motion, this is angular displacement, so it equals to angular velocity times t. So putting that here, so x equal to x0 sine omega t, x equal to x0 sine omega t. Okay, this is the I want to make sure that all this math is beyond your syllabus. Again, only you have to know and use this function. Now, what about velocity and acceleration? Now, remember here we are talking about motion that starts from equilibrium position. So this is a motion start from equilibrium position. So also we want to come here, displacement equal to x equal to x0, as we have seen, sine omega t. So this is a sine function, x equal to x0 sine omega t. If we go to a simple pendulum, this means that for example, the motion is starting from here, this position, x equal to x0, let's call it 0, and this is the maximum point A. So at here, at t equal to 0, here we are, at t equal to 0, our x equal to 0, yes? Now, when we are going here after t over 4 here, so we are going from 0 to a at t equal to t over 4, our displacement will become maximum, so we are at x equal to x0. Okay, now what about velocity? You know from math that if a function of, we have a function of y equal to sine theta, the derivative of y with respect of theta will be cos theta. And similarly, if we have a function of cosine theta, the derivative of the function with respect to theta is minus sine theta. Now, again, you have only to know the equation and how to use it. These derivations are out of your syllabus, but just to understand what we are doing. Now here we will come to the velocity. How to get the velocity? We know that v equal to the change in displacement over the change in time. So this means that let us write it here. Okay, our velocity equal to change of displacement over change of time. This means we have to derive, like here, we derive this function. We have to derive the function of displacement with respect to of time. So it will become, the derivation of sine is cosine. This will be x naught cosine omega t, and because we are deriving with respect of time, so we will get here omega. The most important thing that you have to know that here v equal to x naught omega cosine omega t, and this, as you have here, this is the maximum displacement, which is the amplitude. Also, this is the maximum velocity, which we can write in terms of v naught. So we will have here v equal to, all this is v naught cos omega t. So v equal to v naught cos omega t. This is v naught. Okay, now let's us here talk about, again we are back to our diagram here. When t equal to 0 here, when t equal to 0, our velocity is maximum. So we have the maximum value of velocity here. After t over 4 here, the velocity reached to 0. So it's maximum here, when t equal to 0 here, maximum. Here, v will be 0. So it is starting from maximum value till 0. Now, what about acceleration? Now, as you know here, that the acceleration is the change of velocity over the change of time. Then we have to derive this equation. So, and the derivative of cosine is minus sine. Here, you know the derivative of cosine is minus sine theta. So what we will get here, we will get here x naught omega sine omega t with a minus sign, and the derivative of omega t is omega, so we will get here omega square, and this is very important to know. So the important point here for you is, again, just to use the function a equal to minus omega square x naught sine omega t. This is for displacement, velocity, acceleration. Why this minus is coming? Because the derivative of cosine is minus sine from here. Now, again, you have to know that this is the maximum value of acceleration, omega square a naught. This is omega square x naught. This will give you a naught. So this is the maximum value of displacement, and this is the term all is maximum value of velocity, and this is the maximum value of acceleration. So let's come here again. When t equal to 0, our displacement is 0, our velocity is maximum, our acceleration also is 0. When after quarter an oscillation here, our displacement is maximum, v is 0, and this is also maximum, but in the opposite direction of displacement. So a is maximum here at the extreme right position. So remember that when displacement has maximum value, also the acceleration has its maximum value, but in opposite direction. This is a positive and this is negative, and this will take us again to a is proportional to x with negative or opposite direction for simple harmonic motion. So that's why if the acceleration, the displacement has a sine function, also the acceleration has a sine function, but with an opposite direction. And when displacement is sine, velocity will be cosine. Okay, I think this kind of comparison maybe makes things very simple for you or clear, but the important thing to know these equations and how to use them. And we are talking about motion start from x equal to 0. Now again, we want to make clear that this is omega t is theta, which is in radian. Okay, so what about if the motion starts from maximum displacement, x equal to x naught? Then we have to know that the displacement not only always is a sine function, it can be a cosine function, and the velocity will be a sine function. It depends where is our starting point, from where the object is starting its motion. So if we are here starting from maximum, this is our equilibrium. If the motion is starting from maximum here, so this is our starting point, t equal to 0, it means that x equal to x naught, its maximum value. This will give us a function of cosine for x. So it is x naught cosine omega t. What about velocity? Here our velocity is 0. So velocity will start from here. T equal to 0 here, velocity is 0. So it will give us a sine function for velocity, but in minus sign. Why? Because, okay, so our velocity is equal to minus x naught omega sine omega t. From where this minus is coming, as we have seen before, the derivative of sine is minus sine. What about our acceleration at this point? Here, our acceleration is maximum. Our restoring force is maximum. Yes? So, it's maximum, but in opposite direction from that of displacement. So, if the displacement has a positive direction, this will have a negative direction. What about quarter and oscillation here? When we are here, displacement will become 0. So, at t equal to t over 4, displacement will become 0. Here, our velocity is maximum. So, we are here. And our acceleration again is 0, 0. So, this is our starting point here. Maximum displacement. We are moving for the first quarter oscillation from here to here. So, this will give us a function for acceleration. It will be a cosine function again, like the displacement, okay, but with minus sign. So it will be minus x naught omega square cos omega t, and from where this is here, acceleration is the derivative of v, the derivative of sine is cosine, and we have already a minus sign. So again, what you have to know here, you only look from where the motion is starting. Back to our slide, if the motion is starting from equilibrium position here, so our displacement is 0, our v is maximum, a is 0. So this is a sine function, cosine function, a minus sine function, if we are moving from 0 to right. If our motion is starting from maximum displacement here, at t equal to 0, the displacement is maximum, v is 0, acceleration is maximum, but in an opposite direction from that the displacement. So this is a cosine function, and this is a sine with minus sign here, because the derivative of cos is minus sine, and this is a minus cosine function. Now, here again, acceleration is proportional to the displacement and in opposite direction. And it is so clear from here again, this is the maximum displacement, maximum velocity, maximum acceleration. So our maximum acceleration is equal to minus x naught omega square. So here our acceleration, it means minus x naught omega square. And as we have seen there, that whenever the displacement is increasing, the acceleration also will increase, but in opposite direction. So this will give us the gradient of A with if we are plotting A with x, we have acceleration is equal to minus x naught omega square, for example. Okay, here the gradient of the graph of A against x will give us the omega square. Here, this. Now, let's go for the equations of velocity. As we know that our v equal to v naught cos theta, we want to come to this relationship or equation. Okay? Now, as you know, that if our motion is starting at t equal to 0, x equal to 0, so we are starting from equilibrium position, so we can get x equal to x naught sine omega t. Yes? And our v will be equal to, as we have seen before, it is x naught omega cosine omega t. Okay, let's add, just to come for this equation, we will square the first function, so it's x square equal to x naught square sine square omega t, and this is our first equation. And also we are going to square the velocity, v square equal to x naught square omega square cos square omega t. This is the second equation. Okay, let's make it similar to what we have for displacement, similar to this. So we can write it v square, so we want only x naught here, so v square over omega square equal to x naught square cos square omega t, and this is our equation number 2. Now if we are going to add both equations, so 2 plus 1, what we will get, we are going to add both left sides, so v square over omega square plus this x square. Also we are going to add this with this side. There is a common factor which is x naught square, so x naught square. We will end with cos square omega t plus sine square omega t. Yes, this will give us 1. So we have v square over omega square plus x square equal to x naught square. Taking x to the other side, okay, we'll give, so we'll get equal to x naught square minus x square. Again, we want only v here, so this will give us v square equal to omega square, taking omega naught to the other side, multiply by x naught square minus x square. Now for v, take square root of the right side, it will give us omega square root of x naught square minus x square, and this is, of course, there will be a positive or negative sign here, so it is the value. So we have to calculate velocity either using v equal to v naught cos omega t at any time when the motion is starting from equilibrium point, or we can use only by knowing the displacement, okay, we can get the value of velocity. Now, here are some questions. For example, we have used the graphs here. We have x with time, v with time, and a with time, and all with SI units, meter per second square, and here we have the unit of second for time. We are asked here use the diagram in the figures to determine the values of the following quantities. Amplitude. Okay, of course we are going to see the graph of displacement to get the amplitude. Where is the maximum displacement we have here? This is the maximum displacement. So it is 0.02, yes. So A, maximum displacement, which is amplitude, is 0.02 in the unit of meter. What is the time period? B, the time period is the time for one oscillation. So it's here 0.4 second. Again here it's 0.4 second. Again here it is 0.4 second. So of course this is displacement, velocity, and acceleration for a certain object which is moving in simple harmonic motion. Starting from the starting point is the equilibrium position. What about the maximum velocity? Here we have the maximum velocity, which is 0.3. Yeah, so V naught or V max equal to 0.3 meter per second. What about the maximum acceleration? We come here. This is the maximum acceleration, which is 5. Okay, so V equal to, as a value, 5 meter per second square. Okay, now state at which, here number 2, state at which point, what point in an oscillation the oscillator has zero velocity but positive acceleration. Okay, zero velocity here, but here zero velocity but with negative acceleration. But if we come here, zero oscillation, zero velocity, but with positive what? Acceleration. So it's here. What is the point here? This is the point at t equal to 0.3 seconds. Yes? And look at the xt graph here. When t equal to 0.1, where is this is 0.1, t equal to 0.1. What is the gradient of the graph? Okay, the gradient, you know that the gradient of the graph, what means the slope dx over dt. Okay, here is this. So the gradient should give us the value of velocity. So at t equal to 0.1, here the velocity is 0. So at t equal to 0.1 second, okay, now what is the gradient of the graph? Here the gradient equal to velocity at that time, which is equal to 0. And it's very clear that at this point here, the graph for displacement at its peak value. So it's very clear that there is no gradient here. Okay, this is also a question. Shows the this is a graph which shows the displacement time. Okay, graph for an oscillation or oscillating mass. Use the graph to determine the following: the velocity when t equal to 0. Here we have the displacement when t equal to 0. This is the displacement in centimeter. We are asked to calculate the velocity in centimeter per second when t equal to 0. So when t equal to 0, x is maximum. This means that the velocity should be 0. Okay, for b, because when x is a cosine function, v should be a minus sign function. So here at t equal to 0, v equal to 0. The maximum velocity in centimeter per second. As we know that the maximum velocity is omega x naught. Going back to our equations, this is the maximum velocity, x naught omega. So it is x naught omega. So we have to know our omega. Our omega is related to t, time period. So omega equal to 2 pi over t. And where is our t? Here, the object is completing half an oscillation. Yes, this is a quarter, this is another quarter. So if half of the oscillation is, so it's t over 2 equal to 2 seconds, it means our t is 4 seconds. Yeah? In other words, or you can say that from here to here, we have only 3 over 4 of the oscillation from here. So 3 over 4 of the oscillation have been covered in 3 seconds. This means that our t equal to 4 times 3 over 3. So this means again it is 4 seconds. So we did that in 2 ways. But the simplest way is that to know that this is half an oscillation in 2 seconds, so the full oscillation is in 4 seconds, so this is the time period. So our omega equal to 2 pi over 4, which will give us pi over 2, which will give us 1 pi over 2. Okay, so pi over 2, which will give us the omega equal to 1.57 rad per second. Now, C, the acceleration in centimeter per second square when t equal to 1. Where is 1 second? Here. T equal to 1 second. At t equal to 1 second, displacement equal to 0. Displacement is equal to 0. That means also the acceleration should be 0. Yes? So let's go to the next question. The following equation gives the velocity of a mass spring system oscillating in simple harmonic motion. So we have this equation where v in meter per second, t in second. We are asked to calculate the angular frequency, the time amplitude, frequency, time period, and velocity at t equal to 0.12 seconds. Now, here we have to write the equation for v. V equal to x naught omega cos omega t. Yes? Comparing these two equations, angular frequency. So where is our angular frequency omega? It's so clear that our omega is 10 pi. This is t, and this is the value of omega, the coefficient of t, 10 pi. So our omega is equal to 10 pi, which is 31.3.4 rad. How to get the amplitude? We know that this is the term that will give us the value of the amplitude x naught. So we have here this is the value of x naught omega equal to 9.42. And we calculated the value of omega, so we can get the amplitude x naught is 9.42 over omega. So it's 9.42 over this value of omega, 31.4, which will give us the value of x naught, which is 0.3 meters. Now, the frequency, C, the frequency is related with the angular frequency by this formula, as we know, because omega equal to 2 pi f. So this is our f. So only we have to substitute the value of omega, 31.4. So it's 31.4 over 2 pi, and we are substituting with our pi by 3.14. So we will get the value of f as 5 hertz. Okay. Now, what about time period? Time period. So for D, our time period is the reciprocal of f. So it's 1 over 5. So we will get 0.2 seconds. What about velocity at t equal to 0.12 seconds? Now we are given a certain time and we have to calculate the velocity. So we have to substitute in this function. So we have here our velocity at t time, t equal to 0.12 second. We can write the equation v equal to here it's 9.42. Let's get a wider area. So here we have for E at t equal to 0.12 second, v equal to, now substitute in the given equation, 9.42 cosine 10 pi times, substitute t with this of a given value 0.12. But you have to be very careful here that the angle here is in radian. It's 10 pi times 0.12. The angle here is radian. Omega t, the angle omega t is in rad. And usually our calculators are in the mode of degree. So we will change this theta or angle from radian to degree. To change from radian to degree, we know that we have to multiply by 180 over pi. There is another way that you change the mode of your calculator, but to be safe, I think it's very easy to keep your calculator and only change here your angle. So still we are here, x naught 9.42 cos 10 pi, we are only substituting with the value of t, which is 0.12, and changing this to degree. We have to multiply by 180, divide by pi. Pi will go with pi. So we will get here v equal to minus 7.62 meter per second. This was the end of the lesson for today, but I want to make some clarifications for simple harmonic motion. Although the following equation that I'm going to write are not mentioned in your syllabus, but I think they are very important to be related in simple harmonic motion. As a simple harmonic motion for a pendulum, simple pendulum, now the time period is equal to 2 pi root square of L over G, where L is the length of the pendulum from the center of this object to this point. It's the length of the pendulum, and G is the gravitational acceleration. So this shows us that the time period depends on the length of the pendulum. How it's related? It is related to the length, t, 2 pi, and g, they are constant if we are doing our experiment in the field of our gravity or any constant field. Okay, so t is proportional to root square of L. It means that t square is proportional to L. The importance of this equation is we can calculate the value of G using this formula. So by doing an experiment to get for different L's, we can calculate different time period. So if L, okay, is plotted or t square plotted versus L, we have to get this kind of line, straight line. T is proportional to L. T square is proportional to L. So we can do an experiment for calculating the time period by for different lengths by dividing the total time over the number of oscillations. Okay. Now, anyway, the gradient of this, or the slope or the gradient of this function, will give us delta t square over delta L. Yes, delta t square over delta L. How to use that for calculating G? If this is our equation number 1, from equation number 1, if we are going to take the, if we are going to square the function itself, so what we will get here, equation 1 square will give us t square equal to 4 pi square L over G. Okay, let's ask, okay, here from here t square over L will give us 4 pi square over G. Yes, and we can here, this is representing the slope. So the slope is 4 pi square over G, and from here one can calculate the value of G. And this is the same also for the case of an object or a mass attached to a spring. Now, for this mass, T equal to 2 pi root square of m over k, where m is the mass, this the value of mass, and k is the hook, the spring constant for the spring, which give us an indication about the stiffness of this spring. So from here also one can get that this time period depend only on the mass if we have the same spring. So it depends on the mass. So t square proportional to m, and we are going to get the same kind of graph here. If we are plotting the graph of t square with m, you can get this straight line. And also the gradient of this line, which is the slope, equal to delta t square over m. This is delta t square, this is delta m. And again, if we are going to be back to this equation, from this equation one can get that okay, t square equal to 4 pi square m over k, and t square over m equal to 4 pi square over k. So k from here is again 4 pi square m over t square, yes, and this m over t square is the reciprocal of the slope. So from here you can get the value of k. So this was the end of our lesson for today. For the next lesson, we are going to talk about the kinetic potential and total mechanical energy for simple harmonic motion. Thank you.